Hi, and welcome to this Concept Bite video which introduces the concept of thermodynamic equilibrium and links it to our understanding of the Gibbs free energy. We have already introduced the Gibbs free energy and how it relates to the total entropy of the universe, and it would make sense that one of the ways to increase the entropy of a system is to have a mixture of reactants and products at equilibrium. This is of course balanced by the heat transferred to the system during the process, or the enthalpy at constant pressure. The equilibrium position of a reaction is the minimum of a Gibbs free energy profile. All reactions will proceed to this minimum position. The driving force is spontaneous for both the forward and backward reaction until the minimum is reached. Delta G standard state is the driving force of the reaction. It is defined as the difference in Gibbs free energy between the pure products and pure reactants at constant temperature and pressure. Delta G is the Gibbs free energy at any point between pure reactants and products. When we are at equilibrium, the driving force of a reaction is zero. When delta G standard state is equal to zero, it says the reactants and products of a reaction are equally favoured. Even when delta G standard state of reaction is positive, the reaction will still proceed slightly because it will proceed until the point delta G is zero. The bigger the driving force of a reaction, the more the products are favoured in the equilibrium. The position of this equilibrium is defined by the driving force of the reaction from pure reactants to pure products. This equation, delta G standard state is equal to minus RT log K, tells us how far a reaction can proceed if it reaches equilibrium. It tells us the maximum amount of product we can get. If the value of delta G standard state is less than 0, the equilibrium constant is greater than 1 and the products will be favoured. Conversely, if the value of delta G standard state is greater than 0, the equilibrium constant will be between 0 and 1 and the reactants will be favoured. The bigger the value of the equilibrium constant, the more the products are favoured. But what is going on a molecular level? Why do the values of delta H and delta S and temperature define an equilibrium? We've previously seen that the population of excited energy levels falls exponentially due to the Boltzmann distribution. This brings in our temperature term. We have already seen that the spacing of the energy levels is linked to the entropy, and the relative position of bottom of the ladders or wells for the reactant and products is the enthalpy of the reaction. So the energy spreads over the energy levels in reactants and products. The equilibrium is a measure of how the energy is distributed over a system. In this example, the enthalpy and entropy of reactants and products are similar, and so the equilibrium has similar quantities of reactants and products. This second example is endothermic. The energy of the bottom of the reactant ladder is of lower energy than the bottom of the product ladder. The spacing between energy levels is similar, indicating that the entropy is similar in both cases, but we can still see that some product is formed, as some product energy levels are occupied. This reaction has more reactants than products, and so the equilibrium constant will be less than 1. This example is also endothermic. However, the energy levels of the products are much more closely spaced, and so there are more possible microstates for the product and a higher entropy. In this case, despite the reaction having a positive delta H, the products are favoured because of those closely spaced energy levels. Here we can see why temperature also plays a role in equilibrium. As we lower the temperature, the net internal energy of the system falls, and so does the populations of higher energy levels. Consequently, we see for endothermic reactions, as the temperature falls, the probability of occupying product energy levels falls and the equilibrium shifts. Seeing these energy levels and thinking about the population of energy levels and the equilibrium, we can see why temperature is the only thing which will affect the equilibrium constant, because temperature affects the occupation of energy levels. I hope that this video has been interesting and that you now have an understanding of how the Gibbs free energy links to the equilibrium of a reaction, and further, by thinking about the energy levels within a system, it helps explain the origin of this equilibrium. As always, if you have any questions, please do not hesitate to ask.